So you're probably looking at this right now, and you can see your face kind of looking back at you. Yeah? And I mean that's all because of something pretty simple that we're all seeing in everyday life. And that's a really important word of it, seeing. It's all about reflection, isn't it? Something that we've noticed as a phenomenon since we were tiny. You go to a mirror and the image reflects back at you. But we just want to start using a few more words and terms to make that a little bit more explicit, to talk about what's going on. So when a wave, because that's what we've been looking at each other, meets a new interface or a boundary, right? So a wave is traveling along through space, and then it interacts with it hits something. It can count as a new boundary, whether that's a wall, whether that is a glass, whether that is a different type of gas, whether that's anything, right? It's going to start behaving in a few different ways. And then these are the three that we're going to start off with, because these are the most fundamental. The wave can either be reflected, meaning that wave, let's hopefully I can draw again. Wave gets to that surface and it bounces off. We can call that reflection. One thing it can do is it can refract. I want to do that in a different color. It can refract. Okay. And what's happening there is the wave actually gets through the boundary. It passes through, but it changes its direction while it's traveling. And then finally, we have the wave can be transmitted, or it just passes through and it's not absorbed, it's not reflected, it's not refracted. And we can think of examples where this happens. So this first one up here, reflected. Oops, I want to choose my red. Reflected, we see when reflection happens, when waves bounce off a planar mirror, like we had at the start of the lesson, where you saw your goofy little face in there. Yeah, that's clearly an example of that wave bouncing off and returning back. Yeah, we can see reflection with a wave in a cave, or a room where there's an echo, a big empty room. Something gets shouted out, that wave, that longitudinal sound wave, travels along, bounces off the surface and returns back to you in the form of an echo. Yeah, we can get it looking at the refracted one now. You can see that in water very easily. Yeah, you can get yourself a cup, dip a pen in there, and it looks like that pen's actually broken apart, because the light waves have changed the direction they're traveling, so it looks like they're in a different place. Creates an optical illusion. Yeah, if anything's got the word optical in, we're talking about light, optics, opticians. Yeah, somebody you go to make sure you can see light correctly, helping out with glasses. And then transmitted, well, that's happening all the time. You've got all this air around us, and the light can travel through it very easily without being absorbed or reflected, and that allows us to see things clearly. A window transmits the light through, allowing you to see what's outside. And of course, the one we're focusing on today is we're focusing on reflection, but all these other fundamentals are really important for us to know as well. So it's good we get a little overview of those before we start getting the nitty-gritty of reflection. So if you've got your own mirror, you could actually do this and and introduce your own mirror and things like that. But I'm going to show you right now, virtually one of the ways of we can display laws of reflection. So first thing we could do is we could have a plane mirror and put it down. We call it a plane because it operates in one plane, like an x-axis or a y-axis, just like a nice straight plane. Typically how we draw mirrors, if we're going to sketch something like this in our books, is we draw a straight line, and then we do this dashed line here. And now these dashes, they're showing you that's like the other side of the mirror. It just gives the reader of this diagram, because remember, diagrams are kind of like their own language. It gives the reader of this just a context of what's going on. Then something else, I'm going to add my dashed line back in there. Something else we can always do on diagrams, because as I was saying, they're their own language to help people out, is we can add something called a normal line. A normal line is a perpendicular line. A perpendicular line. Now, a perpendicular line is a line which is at right angles to a surface. So we've got our nice straight plane surface here, because we said this was a plane mirror. And we have this normal existing at right angles here. Now, the normal kind of exists as it's an imaginary line, which is why it's dashed. Yeah, you don't look at a mirror and see this normal sticking out of your face. That's clearly not true. Well, we put this normal line on and we imagine this line and we suppose this line because it helps not only us but our reader have a little bit of perspective and a little bit of sense of direction of what's going on. It's kind of like putting compass directions on a map or something like that. It just gives us like a base to start talking about. We know the normal is here. We know this perpendicular imaginary line is there on the surface. And that's just going to help give us a perspective of where we are. Where are we? Oh, I'm going towards the normal. I'm going away from the normal. Yeah? And it just gives us a bit more of a sense of direction of what's going on in the situation. The normal line's really useful. Let's put these on to remind us it's perpendicular. Now here what I've got in here is I've got a ray of light coming in. Now we're always going to represent our rays of light as straight lines with arrowheads on. And that's just coming straight in to our plane mirror. Yeah? And now it's coming straight into our plane mirror. And because it's reflection, the thing that's going to do is it's going to bounce right off. It's going to bounce, it's going to reflect. Okay? Now there's a few points there, proving that, you know, it's all coming in a straight line, or maybe they're points that we got experimentally from using a ray box or something like that. And he's back in to show that's the side of the mirror, and I'm going to add in my right angles to show that normal perpendicular. Now, what we've introduced here is we've introduced an angle that exists in between the normal and the ray of light. We're going to call that the angle of incidence. The reason we're going to call that the angle of incidence because that first ray of light that comes in, we refer to that as the ray of incidence, right? The ray of incidence, yeah. An incidence being, you know, something that's, you know, moving in a straight line, you know, an intersection of a line, right? And this incident ray we're going to call our first ray that's, you know, appearing in there. So what happens on the other side? Well, we said it was gonna reflect, it was gonna bounce off, right? So let's have a look at this together. And the law of reflection, a law means it always happens, yeah? It always happens all the time. There's our mirror, and I've got our dashes in now perfectly already. We're gonna get, come on. There we go, my normal, my perpendicular imaginary line to help us know what's going on. I have my ray of incidence coming in, my incident ray. And then out of that, we're going to get a new ray bouncing off. A bounced off ray. A ray produced by reflection, or reflected ray. It's really that intuitive and that obvious. Okay? And then we can start talking about our angles. The angles between the ray and the normal, like we looked at before. Now that one's called the angle of incidence, because it is the angle that comes between our normal and the incident ray, right? And this other one here, well, that's going to be called the angle of reflection. Yeah? Now, something you'll notice here, you'll notice a relationship between these two angles. The angle of incidence and the angle of reflection are exactly the same thing. And if we're getting this nice perfect reflection here, that's what happens. The angle of incidence equals the angle of reflection. And because those two angles are the same, it's why we're not getting distorted images. Yeah? That's one of the reasons we're not getting distorted images, because we have a nice plane surface, and because the angle of incidence equals the angle of reflection, the angle of incidence equals the angle of reflection, the angle of incidence equals the angle of reflection. And if you can remember that fact that the angle of incidence equals the angle of reflection, you'll be able to draw this diagram from that one fact. You'll be able to remember how this looks and how we can display this, because you know the angle of incidence equals the angle of reflection. Now, here's two different types of reflection that we can have. And in each of them, we're getting the angle of incidence equaling the angle of reflection. Yeah? But we're getting two overall results. First one, we've got this boy. He enjoys staring at the nice flat ground, and he's seeing that perfectly because he has that smooth surface, and all of those rays of light are able to bounce off that in a uniform fashion. Uniform meaning all the same. Yeah? All of them bouncing off and off there. Uniform. Now, the second girl over here on the right, she likes to stare at this bumpy ground. Now, the light rays she's getting off there, they're bouncing off in every different direction. They're scattering around. Yeah? So from our smooth sections that the boy was looking at, smooth surfaces give us something called specular reflection. Think specular, like spectacles, optics. It's all about opticals. It's all about opticians. It's all about spectacles. It's about glasses. Specular reflection. You get specular reflection. That's what we're getting most of the time. Yeah, we're getting specular reflection off surfaces all around us here, and that allows us to see things really clearly. Now, this girl on the right, all of her light is scattering around. It's diffusing, like diffusion as things spread out. She's getting diffuse scattering from that rough surface that's going on there. Now, an analogy I like to think about, try and remember these, as you can think about, and you'll even do this if you carry on your physics further and further. You can start to think of rays of light as little packets of energy. Yeah, photons are called. And we can think about this ray of light being all these little packets of energy, being these photons. We can think of those as little balls. So let's think about our light now as a little ball, as a model to help us out. And think about if you went with a little bouncy ball, you went with a little ball to like a park with a nice smooth surface, and you bounce that ball down that smooth surface, you'd know exactly where it was going to go. You'd be able to predict really easily with your brain because you know it's going to specularly reflect. You know it's reflection, you know it's bouncing from a smooth surface, and you're going to get specular reflection. Now you take that same ball and you take it to some ground that's really rough and really bumpy and really rocky, stuff like that. You throw that ball, you throw that ray of light, you throw that packet of light, you throw that photon, you throw that down onto the bumpy, rocky floor. It could go anywhere. You have no idea where it's going to go because it's going to scatter. Because reflection from a rough surface results in diffuse scattering. That's what happens, right? So here's a quick little word fill activity. I would pause this. I would have a go through this. If you have any problems, put these in the comments. But I think this one should be pretty easy for us to do. And it's something that could support our notes and our diagrams we've already made on the topic of reflection.